In this video, I'll talk about the very fundamental concepts associated with circuit analysis: charge, charge motion, and electric fields. These are necessary to understanding what we'll be doing in this course, but we don't need to be proficient in calculating, for example, electric fields. We just need a general idea of the concepts involved. Charge is the basis of electrical circuit analysis. The primary goal of electrical engineers is to move charges around to perform a given task. No matter what we're doing with electricity, we have to move charges. Usually, the smallest unit of charge that's useful to us is a single electron. This is because electrons are less closely tied to their parent atoms, so we can move charges from one atom to another to get them where we want them to be. Units of charge are coulombs, abbreviated as C. 1 coulomb corresponds to the charge in 6.2 times 10 to the 18th electrons. Notice that there's a negative sign associated with this. The charge of an electron is negative, but a coulomb's a positive charge, hence the change of sign. If we invert this number, it turns out that one electron has a charge of negative 1.6 times 10 to the minus 19th coulombs. The charge of a single electron is really small, so to do any useful work, we tend to use a lot of electrons. Any material is composed of both positive and negative charges in the form of protons and electrons. The total charge on a material comes from an imbalance between the positive and negative charges. A charge creates an electric field which affects other charges. The phenomenon is like the gravitational field created by a mass. The gravitational field of one mass affects other masses in its vicinity, which is why the moon orbits the Earth. An electric field, commonly called an E field, is a vector field. It has both magnitude and direction. A point charge, for example, creates an E field that radiates outward from the charge. The strength of the field is proportional to the size of the charge and reduces with the square of the distance from the charge. Mathematically, the E field is proportional to the charge, Q, and inversely proportional to the distance, r squared. This r with a hat over it is a unit vector pointing radially away from the charge. That gives us the direction of the electric field. As I've already said, the electric field is analogous to the gravitational field of a mass. The gravitational field is proportional to the mass and decays with the square of the distance. The main difference is that a gravitational field is toward the mass, as indicated by this negative sign. So it tends to pull other masses toward it. An electric field, on the other hand, repels other positive charges that are placed in its vicinity. As I mentioned, the electric field induced by a charge, Q1, will exert a force on other charges, say Q2, which are placed in its vicinity. An equal and opposite force is exerted on the original charge. Coulomb's law says that the forces on the charges are proportional to the product of the two charges and inversely proportional to the square of the distance between the charges. If, as shown here, the two charges are either both positive or both negative, the force repels the charges from one another. If the charges have opposite signs, the force attracts them to each other. As engineers, we tend to be concerned with doing work, which is just a form of energy. Moving a charge in an electric field results in energy transfer. Suppose we have a charge Q1 that creates an electric field, and we place another charge Q at a distance B away from Q1. Because of the effects of the field, there's a force applied to Q. Now, let's move the charge Q along some path S to a position A. Since there's a force on Q, this corresponds to moving a force through a distance, which is the definition of work. The work involved in moving the charge from point A to point B is the integral of the dot product of the force times the distance. This is just a change of potential energy of the charge. The potential energy change associated with moving a charge in an electric field is generally represented by the variable V. So the change in electric potential resulting from moving the charge from point B to point A is delta V sub BA, where delta signifies a difference in some parameter. Keep in mind that this is a difference in energy between two different points in space. This energy change is sometimes called the electric potential energy or just the electric potential, but it's more commonly referred to as voltage. There are a few things we need to keep in mind about voltage for later. First, it's always a difference between two different points in space. Voltage at a single point without moving the charge is meaningless. This change in potential energy provides a force that can be used to move charges around. For this reason, it's also called an electromotive force, or EMF. Those are the basic ideas relative to charge and charge motion that will be important to us in the near future. We won't be working directly with charge, electric fields, and Coulomb's law. In this class, we're mostly interested in energy transfer, or using electricity to do work. So we'll be interested in the energy associated with moving charges around. This is more easily done in terms of secondary variables: voltage, which I've just introduced and we'll talk about more in the next video, and current, which will be introduced in a later video.